Okay, so in this final video on model selection or tools for model selection, I'm going to talk about grid search. So the question that we are essentially asking here is, how do we search for two or more optimal parameters? So for instance, when we work, as we should do when we work with ElasticNet. So as you might remember, then we have worked quite a bit with both lasso and ridge regression, and then a couple of times I've mentioned that ElasticNet is basically a combination of the two, where we are penalizing both the absolute value of our coefficients or our weights, but we're also penalizing the squared value. So we basically have two penalty hyperparameters that we want to choose or choose. Okay, so more formally, the goal is that we want to find the parameter combination such that we are minimizing the mean square error with this ElasticNet. So option one is we can loop over the joint grid of parameters. So we basically get a grid because we have a certain, say, range of values for lambda 1 that we want to try out, but we also have a certain range for values of lambda 2 that we want to try out, and then this basically, then we get lots of different combinations that we want to try out, and this is basically a grid, right, of combinations. So we can loop over this joint grid of parameters, and then we can basically estimate and evaluate a model for different parameters, for different parameter combinations. So this is obviously something we can just do, right? But the problem here, the caveat, is just that it's manual, and then it can be extremely tedious. So it can involve a lot of code, but if you have a lot of parameter combinations, or if you have a lot of data, this can just take long time, and you don't want to do that. Or it could take be very computationally exhaustive. So another option is that you use a grid search CV that comes with scikit-learn, and this has a tool that tests all parameter combinations. Okay, so how does this look in Python? So in order to get an idea of that, we import grid search CV from model selection in scikit-learn, and we import ElasticNet from linear model in scikit-learn. So we want to try this grid search CV out and see how it works. So in order to do this, we want to first create a new pipeline that's associated with ElasticNet. So we create pipe EL using make pipeline that we have seen several times before now. Then we specify that we want to use polynomial features, want to use a standard scalar, and then we specify that we want to use ElasticNet. Then we create this GS object from grid search CV, where we specify that we want to use this pipe EL that we specified up here. And then what we're doing here is that we basically, again, we implicitly loop over different values of lambda, similar to what we have done in the previous videos. But then what we're doing here is also that we are basically trying out different weights of penalties between between the penalty associated with lasso and the penalty associated with ridge regression. So L1 and L2 penalization. So that's basically our two. In practice, that would be our two sets of hyperparameters. So it's basically the penalties and the relative weight of penalty that goes into these two types of penalizations. Then we're choosing our scoring measure, and we're specifying that we want to use a cross validation. Then we're also specifying some other things that are not too important here. And then we fit a model, an ElasticNet model, on our development data. Okay. Okay, so what does this now yield? So what we can see here is that we basically get that the optimal parameter combinations that we got out of using grid search CV across different lambdas and different alphas, so these different weights between different types of penalization. When we evaluate this model on our test data set, we get a mean square error of 11.1. Okay, so actually we can see that this performance is slightly worse than the performance that we got up here, but still much better than this. But I think this is pretty much within the same range as this. This could really just be random that we get a slightly worse performance here, but it's clearly also not better, right? So that's basically how you apply grid search CV in order to obtain an optimal parameter combination. So here we can also see the parameters that we got out of it. So we can see that the ratio of weighting was in fact 0. So I think, as far as I remember, this means that we basically have ridge regression, and this was our penalty parameter. Okay, so what do we then do if we have 10,000 parameter combinations? So something that will take a long time to loop, basically to loop through and use cross validation on. This will obviously take a long time, and it will be very computationally exhaustive. So one option is that you can buy a cluster on Amazon and learn how to parallelize this process across computers. So you can buy multiple clusters. That's not feasible in this course, but it is something you can do, but it's not feasible in this course. You can also try and drop some of the parameter values, but the question is really just which of them do you want to drop. You need to have some idea of where the optimal parameter combination roughly is, and sometimes you might not really know that. And then finally, you can use randomized search CV that searches over a subset of parameter combinations using some kind of a pre-specified distribution of parameters. And then finally, just a brief comment about how we obtain the coefficients from our models. So this can be fairly useful in some instances. How do we do that? So we can actually first access our model from our pipelines, just referring to a pipeline, and then the step that's associated with the model. And then we can write .coef underscore, and then here I'm just getting the first 13 coefficients from this model. And what you can actually see in this case is, I guess this is actually interesting enough, is that in this case we have used Lasso, and we can see that Lasso indeed does what we expected it to do. It sets lots of the coefficients or weights to 0. Okay, so this is how Lasso regularizes instead of sort of squeezing them towards 0, as you could argue that Ridge is basically doing in many cases. Then Lasso typically just sets the weights or the coefficients to actual zeros.